Hi everyone, my name is Amal Narayanan. I'm a student of Department of Polymer Science at the University of Akron. Today I'll be presenting my work on mimicking nature strategy for creating strong underwater adhesives. This is a part of ACS Poly Excellence in Graduate Research Virtual Symposium series. Here I will introduce two concepts of adhesive science. So the first one is the interfacial part. So the interfacial interactions means the interaction between the polymer and the substrate, which you can call as a thermodynamic work of adhesion. Second is the cohesive strength, which is the interaction within the polymer, which is a kinetic factor. If you want to make an adhesive which sticks better, you need to optimize both these components, the thermodynamic and the kinetic factors. So Alan Jen from University of Akron has derived this equation in 1996, and people have used this concept to create several varieties of adhesives. But all those adhesives fail to stick in underwater conditions because water can deteriorate the adhesion through four major mechanisms. First, the swelling and plasticization, which will kill the adhesive's cohesive strength. Second, the weak boundary layer, which kills the interaction between the polymer and substrate. Then wicking and crazing and erosion and hydrolysis are two other mechanisms through which water can act as a barrier for adhesion. Hence, the adhesion underwater is extremely different from the dry adhesion. Why are people interested in developing underwater adhesives? Because it has several areas of application. The first one being the tissue engineering, where if you can think of a bleeding injury, you can put an adhesive instead of putting sutures, which will help you for scarless wound healing. At the same time, wearable electronics and underwater construction are another major industries which will be benefiting out of the underwater adhesives. These three areas are places where the presence of water is inevitable. So there's a high need for adhesives that can stick underwater. Though man-made adhesives fail in underwater conditions, nature has developed several underwater adhesive specialists which can stick underwater conditions. Sandcastle worms and mussels are the most famous one among these. In the next slide, I'll be focusing more on the mussel adhesive aspect. So what does mussel do? Mussel has its feet through which it can find the surface in underwater conditions. And this feet has several proteinaceous glands which secretes liquid proteins, which is known as muscle food proteins. And these food proteins solidify to become the byssal thread. These byssal threads, as you can see here, is cured, and it has if several of these byssal threads are created by muscles in order to sustain its life in underwater conditions. So what makes muscle food protein special? Here's the molecular structure of one of the muscle food protein. You can see here there is several series of post-translational modification in here, which means this proteins has been post-translationally modified to form 3,4-dihydroxyphenylalanine, also known as DOPA, with the catechol groups. In our previous studies, we have shown that these catechol groups can form multiple acid-base interaction in a localized site called as multimodal acid-base interactions. This allow these protein to stick in underwater conditions. Another aspect which is very important for these bioinspired adhesives is its delivery. So sandcastle worms has a special way of delivering its adhesives. It secretes a series of positively charged and negatively charged proteins, which when mixed together in a neutral pH forms droplets like these here, and with time it settles to form two different phases, known as dense and dilute phases. Recently, mussels also have been shown to have this mechanism to deliver its food proteins. The interesting part about the mussels, is that its ability to self-coacervate, which means it only needs one component. These are two identical components, and it forms coacervation even without the secondary mixture like the sandcastle worm. At the same time, humans also interestingly has this phenomena in several organelles. One such is a propoelastin. This propoelastin is a protein which undergoes this such droplet to dense phase transition with temperature. This propoelastin has a LCST temperature in water, which helps it to form these droplets and then to the dense phase. And the unique properties of this dense phase is a low viscosity and ultra low interfacial tension under water conditions. Inspired from the sandcastle boom adhesives, several groups have synthesized positively and negatively charged polymers and mixed them together to create coacervating polymers. And they have been successful in achieving strong underwater adhesion. Recently, after the discovery that one of the muscle food protein self-coacervates, people have attempted to synthesize polymers which can undergo self-coacervation. Unfortunately, both these components still requires a presence of cationic or anionic polymers, which has high cytotoxicity and high pH and salt insensitivity. The problem with these three are in a real life situation where if you are using such adhesives for tissue adhesion purposes, it is a wet and dynamic environment where the pH and salt is not balanced always. In such cases, these polymers may not be effective. Hence, there's a need of adhesives which can be coacervated without the presence of a secondary component, pH or salt. In my study, we have created a propoelastin-like polyester which has LCST-driven coacervation. These polymers dissolve in temperature below its LCST, and above its LCST it forms these nano droplets which later condense to form this dense phase. And this condensed dense phase is water insoluble, and at the same time it has low viscosity and low ultra low interfacial tension. All these properties allow it to spread in underwater conditions. So in my study, we have created this hybrid protein-like polyester, which has two different protein-inspired units. First one being the propoelastin mimetic unit, and the second one being the muscle-inspired interfacial binder, and the third one is the cohesive strength. These proteins, these polyesters undergo lower critical solution temperature based transition at higher temperature, and is stable in all ranges of pH and ionic strength due to its the droplets formed from the polyesters above its LCST condense to form these dense and dilute phases. The interesting properties of these dense phases are several, among which low interfacial tension, as you can see from this image, is a very unique property. At the same time, these hippos or the hybrid protein like polyester show higher contact angle on hydrophobic surfaces in underwater conditions, which helps to spread these adhesives in underwater conditions without sticking onto the pipe tips. Also, if you look at the viscosity of this material, if you look at this, the left side, which is the original polymer before it is dissolved, it has high viscosity compared to the dense phases. And the dense phase also show shear thinning behavior, which helps it to spread effectively in underwater conditions. Polymer to spread underwater. As you can see from this video, these polymers, the dense phase of these polymers are easy to spread in underwater conditions, as you can see here, and it absorbs on the hydrophilic surfaces efficiently. And you can later cure this material using UV light, and it acts as a strong underwater adhesive, as you can see from the adhesion measurements here. Two methods of adhesion measurements were used. One, the lab shear on the top, and the second one is the tack adhesion measurement. This was completely done, spread, cured, and sheared in underwater conditions. And it shows one of the most strongest coarse-based adhesives reported in the literature with such rapid curing. So from this talk, I hope everyone learned that muscles orchestrate strong underwater and adhesive mechanisms through its molecular and macroscopic methods. It has perfected both the chemistry and the delivery of the adhesives in underwater conditions. The polyesters that we have developed is non-ionic nature, which helps it to be pH and salt insensitive, which was never been reported before in the literature. And we anticipate that the strong adhesive nature of these non-ionic polyesters will help in sealing wounded tissues. With that, I would like to acknowledge my advisor Ibrahim Joy, my strong collaborator Ali Dinojwala, and Dr. Chinhoy Liu and Joshua for their help during this work. Also, I would like to thank ACS and ACS Poly Division for organizing this virtual symposium. And if you have any questions, please forward it to this email address or through Twitter. Please feel free to contact me. Thank you.